All right, so moving on to the next question, and it's obviously question 3 as it says up here. So we've got a function g of x, and g of x is 2 sine 2x, and we want to state the range of g. Okay, so we're looking at the range of g. All right, so key thing here is we're looking at sine, and so the range of sine is between -1 and 1, regardless of whatever this angle bit might here be. In this case, it's 2s for this question, but regardless of that, whatever the angle is, the biggest value you can get for sine is 1, and the smallest is -1. So we've got a 2 here. So the range of which is a dilation, of course. So dilation on this range. So the range of G is -2 to 2. All right, 1 mark. And that's all we need. All right, the next is the period. So period, this other 2 here in front of the x there is involved in that. And so, of course, the period for sine and for cos is 2 pi over n, and n in this case is 2, so 2 pi on 2, so our period is then pi. All right, again, 1 mark for both of those, so nothing really, anything more required. All right, this next one, however, is a 3 marker. So there's some working out that is required. Now, we've got to solve 2 sine 2x, so that's the thing that was up there, is equal to √3. For x is an element of R, okay? So now there's no domain restriction on x here, so we've got to give all angles. All right, so that'd be the general formula. So all possible angles here with that R. All right, so let's have a look first of all. So 2 sine 2x is equal to √3. And from that, we'll go that sine 2x is √3 on 2. All right, and so when we're looking at this, we've got a value of √3 on 2, and we know that the sine -1 of √3 on 2 is pi on 3 as a reference angle is what I call it. So we're looking at somehow or other this pi on 3 being involved. All right, so just down here, I'm going to do this down the bottom here. So if we've got our circle, our unit circle, very rough one, and we're looking at sine. Now here, sine 2x is √3 on 2. It's positive, and sine is positive in the first and the second quadrants. So we're looking at angles, possible angles there. Now that pi on 3 that I was talking about before, it's this size there, but this here is also pi on 3. All right, now in this case, because x is an element of R, we're wanting all angles, so we can spin around in circles all we like. So for this first quadrant angle, we're going some multiples of 2 pi plus a bit more. All right, so even pi's, even multiples of pi plus a bit more. So our angle bit, the 2x, so the 2x is for this first angle is 2k pi, where k is some number, and then not just any random number, it's actually an integer, plus pi on 3. And so that k is telling us how many times we're spinning around the circle. All right, we don't spin at all. We spin once, we spin twice, we spin backwards, whatever. But whatever, doesn't matter. We end up at this positive axis down here, plus our pi on 3. All right. Now the other one is odd multiples of pi minus. This is one way of describing it. So odd multiples of pi minus pi on 3. So odd multiples of pi minus pi on 3. Now, how do we get an odd number? Well, 2k gives us an even number. And if we add 1, or even if we subtract 1, but I'm going to add 1, doesn't matter. If we add 1, we'll get to an odd number. So if k is 0, 0 plus 1 is 1. If k is 1, 2 plus 1, 3. So we're getting to an odd multiple of pi, and then we're taking pi on 3. All right, and so that's for 2x. So I could write in here 2x equals 2k pi. Let me get rid of that horrible looking thing. All right, so now I've got to do some rearranging. Over here on the left hand one, divide everything by 2, and so you get k pi plus pi on 6. And the other option, oops, it's not 2x, but x, dividing everything by 2, x would be 2k plus 1 all over 2 pi minus pi on 6. All right, then we can rearrange things, and so here we've got pi that's a common factor, so we can go k plus 1/6, lots of pi. And over here, again, there's stuff that we can do with this if we wanted to. So if I put that 2 in, I'll have k plus 1/2, lots of pi, minus pi on 6. Take the pi's out as common factors. I've got k plus 1/2 minus pi, oops, not minus pi, but minus 1/6, because I've now taken the pi out as a common factor, and equals 1/2 minus 1/6 is actually a third. So we've got k plus 1/3 pi. And so there are our things for x. Now, I also should, to be technically correct, say that k is an element of z. So k is an integer, a whole number. All right, there's how we would go that, 3 marks. So there's a significant amount of working, which you can see that there is. But the couple of key things, x is an element of R, so we're wanting all angles, not just the ones in one rotation of the unit circle. And so then we need to use these general formulas, all right, which you can remember or you can work out like I did. All right, and so something that's handy if you want an even number, so 2k will always be even. 2k plus 1 will always be odd, where k is an integer. So if you ever need to generate odd or even numbers in the general sense, there are things that you can use. Anyway, I'm starting to waffle on a bit here, so let me leave that question and move to the next one, which I think I will do another video for, because it